Welcome to week 8 of Fundamentals of Python and Machine Learning. In this lesson, we are covering Chapter 9, Supervised Learning, Classification using K-nearest neighbors. In the previous classification lesson, logistic regression learned coefficients and used a mathematical function to estimate class probabilities. K-nearest neighbors takes a different approach. Instead of learning one global equation, KNN compares a new observation with labeled examples from the training data. It finds the nearest neighbors and uses their classes to make a prediction. During this lesson, we will examine distance, feature scaling, the choice of K, cross-validation, parameter tuning, and the differences between KNN and logistic regression. By the end of this chapter, you should be able to explain how K-nearest neighbors performs classification. You should understand how Euclidean distance measures similarity between observations and how the algorithm uses majority voting among nearby training examples. You will learn why feature scaling is essential for a distance-based model. You should also be able to explain how a very small value of k can overfit the training data and how a very large value can underfit the true pattern. Finally, you will learn how to use stratified cross-validation and GridSearchCV to tune the number of neighbors, evaluate the final model on unseen data, and compare KNN fairly with logistic regression. KNN is a supervised learning algorithm. The training data contains feature values and known class labels. The model uses those label examples to classify new observations. Examples of classification include spam or not spam, approved or denied, one flower species or another, and one customer category or another. KNN can also be adapted for regression, but this chapter focuses on classification. The predicted result is a category rather than a continuous numerical value. K-nearest neighbors is one of the most intuitive machine learning algorithms. To classify a new observation, the algorithm finds the K-training examples that are closest to it. The letter K represents the number of neighbors included in the vote. If most of those neighbors belong to class A, the query point is classified as class A. If most belong to class B, it is classified as class B. KNN assumes that observations located near one another in feature space are likely to share similar outcomes. Whether that assumption is useful depends on the dataset and how the features represent similarity. KNN is often described as an instance-based or lazy learning algorithm. During fitting, it does not estimate coefficients for a global prediction equation. Instead, it stores the training examples and uses them when a prediction is requested. This makes the fitting stage relatively simple. However, prediction can become expensive because the algorithm may need to calculate distances from the query observation to many training samples. Although KNN does not fit a traditional equation, its neighbor voting behavior still creates an effective decision boundary across the feature space. Suppose k equals 5. The algorithm identifies the 5 closest training observations. If 3 neighbors belong to the teal class and 2 belong to the gold class, the majority class is teal. The query point is therefore classified as teal. The algorithm does not ask which class is most common in the entire dataset. It focuses on the local neighborhood surrounding the query. This local approach allows KNN to represent relationships that may not follow one straight decision boundary. The complete KNN prediction process can be summarized in 5 steps. First, receive a new query observation. Second, calculate the distance from that query to the labeled training samples. Third, sort the samples from nearest to farthest. Fourth, select the first k observations. Fifth, count their class labels and assign the class with the strongest vote. Scikit-learn performs these steps for us, but understanding the process helps us interpret the effect of distance, scaling, and the number of neighbors. Each numerical feature can be viewed as a dimension. With 2 features, every observation can be placed at a coordinate on a 2-dimensional graph. With 3 features, the observations occupy 3-dimensional space. With many features, the model operates in a higher dimensional feature space that is difficult to visualize directly. Distance measures how far apart 2 observations are in that feature space. The meaning of near depends entirely on the selected features, their units, and the distance metric. The chapter introduces Euclidean distance. This is the ordinary straight line distance between 2 points. For each feature, subtract one observation's value from the other. Square each difference. Add the square differences. Finally, take the square root. With 2 dimensions, this calculation follows the Pythagorean theorem. With more dimensions, the same pattern continues across every feature. A smaller distance means the 2 observations are considered more similar under this metric. Consider the points p equals 2, 3 and q equals 5, 7. The difference on the first feature is 3, the difference on the second feature is 4. We square those values, producing 9 and 16. Their sum is 25. The square root of 25 is 5. Therefore, the Euclidean distance between these 2 observations is 5 feature space units. In a real dataset, Every feature contributes to this distance calculation. We can implement Euclidean distance with NumPy. First, subtract one point from the other. Next, square the differences, then add the squared values. Finally, take the square root. NumPy performs these operations across every feature. Scikit-learn provides optimized nearest neighbor implementation, so we normally do not write the complete classifier from scratch. However, this small function shows the mathematical calculation behind the algorithm. A simple KNN implementation begins with an empty list of distances. For every training observation, calculate its distance from the query point and store both the distance and class label. Sort the list from smallest distance to largest. Select the first k entries. Count the levels among those neighbors. The majority level becomes the prediction. This approach makes the algorithm easy to understand, but repeatedly calculating and sorting distances can become expensive for large datasets. Scikit-learn can use different search strategies internally depending on the dataset and configuration. Euclidean distance is common, but it is not the only possible metric. Manhattan distance adds the absolute difference across features rather than taking a straight line path. In Scikit-learn, the default Minkowski metric with p equal to 2 corresponds to Euclidean distance. Setting p equal to 1 corresponds to Manhattan distance. The best metric depends on how similarity should be defined for the problem. Distance should match the meaning of the features rather than being selected only because it is the default. Feature scaling is essential for KNN. Suppose one feature is age, ranging from 18 to 70, while another is income, ranging from 20,000 to 120,000. The income differences are numerically much larger. Without scaling, income may dominate the distance calculation even when age is equally important to the problem. KNN does not automatically understand the units, it only sees numbers. Scaling places numerical features on more comparable ranges so that distance is not controlled by the largest measurement scale. We place standard scaler and k-neighbors classifier inside a Scikit-learn pipeline. Standard scaler learns the mean and standard deviation of each training feature. It transforms the feature so that they use a comparable standardized scale. The transformed values then enter the KNN classifier. A pipeline ensures that scaling is learned only from the training data and applied consistently to validation, testing, and future observations. This prevents data leakage and simplifies cross-validation and parameter tuning. To visualize KNN, we can generate a two-class dataset using make-nm-uns. The observations form two curved interlocking groups. The noise parameter adds variation so the classes are not perfectly separated. This dataset is useful because one straight decision boundary cannot represent the relationship well. It allows us to see how KNN creates a flexible boundary based on local neighborhoods. Synthetic data is useful for demonstration because we know how the underlying pattern was generated. Before training, we visualize the two feature columns. Each point represents one observation. The color indicates the known class. The two classes form curved regions with some overlap caused by noise. Visualization helps us understand why model choice matters. A flexible local method such as KNN may represent this shape differently from logistic regression, which begins with a linear decision function, unless additional features are created. We divide the dataset into training and testing subsets. The test set is held back for the final evaluation. The stratified parameter preserves approximately the same class proportions in both subsets. The random state makes the split reproducible. We will tune K using cross-validation on the training data. We should not repeatedly use the final test set to choose K because that would allow test performance to influence model design. The final test set should remain unseen until tuning is complete. We feed the complete pipeline using the training data. The scaler learns the training means and standard deviations. The classifier stores the transformed training observations and their labels. Unlike logistic regression, KNN does not learn one set of coefficients that defines the decision function. Most of its work happens later, when a query observation must be compared with the stored examples. Scikit-learn allows us to inspect the neighbors used for a query. First, the query must be transformed with the same scalar learned from the training data. Then the classifier's neighbors method returns the distances and training set indices of the nearest observations. This can help us understand an individual prediction. However, the nearest points are determined in the standardized feature space, not directly from the original on-scale coordinates. Interpretation should always consider the preprocessing applied by the pipeline. The predict method returns the final class selected by the neighbor vote. The predict method returns class probabilities based on the proportion or weighted contribution of neighbors in each class. With uniform weights and 5 neighbors, if 4 belong to class 1 and 1 belongs to class 0, the estimated class 1 probability is 4 divided by 5, or 0.8. These are local vote-based probability estimates. They should not automatically be interpreted as perfectly calibrated real-world probabilities. The number of neighbors is a hyperparameter. It is selected before the final model is trained. A small value of k creates a highly local model. Only a few nearby observations influence the prediction. A larger k considers a broader region of the feature space. The value of k changes the smoothness of the decision boundary and the model's sensitivity to individual training examples. There is no universally best k. It should be selected using validation rather than guesswork alone. When k equals 1, the prediction depends entirely on the single nearest training example. This can create a highly irregular decision boundary. An isolated noisy observation may create its own small classification region. The model can fit the training data extremely closely while performing less reliably on new data. This behavior is associated with high variance and overfitting. A low training error does not prove that the model generalizes well. When k is very large, the model considers many observations that may be far from the query point. The majority class across a broad region can overpower meaningful local structure. The decision boundary becomes smoother and simpler. If k approaches the number of training samples, the model may predict the overall majority class for almost every query. This behavior is associated with high bias and underfitting. The model becomes too simple to capture the real class pattern. A moderate value of k can balance local detail with stability. It may preserve the main class structure while reducing sensitivity to individual noisy points. The goal is not to create the smoothest possible boundary or the most detailed boundary. The goal is to find a value that performs consistently on unseen observations. Cross-validation helps estimate that performance across multiple data partitions. For binary classification with uniform voting, choosing an odd value of k can reduce the possibility of a tight vote. For example, 4 neighbors can split 2 against 2. 5 neighbors must produce a majority when there are only 2 classes and every neighbor has one equal vote. However, this is a heuristic rather than a universal rule. Multi-class problems can still produce ties without k. Distance weighting can also change the voting process. Cross-validation is more reliable than selecting k, only because it is odd or because it follows a simple formula. By default, KNN uses uniform weights. Every selected neighbor contributes equally to the vote. With distance weighting, closer neighbors receive more influence than neighbors located farther away. Distance weighting can help when the nearest observations are more informative than the rest of the selected neighborhood. However, it can also make the model more sensitive to extremely close or duplicate observations. Both the number of neighbors and the weighting method can be treated as hyperparameters and evaluated through cross-validation. These decision boundaries illustrate how k and the weighting strategy change the classifier. K equals 1 creates a highly detailed boundary. A moderate k produces a smoother region. A large k may oversimplify the curve pattern. Distance weighting can preserve more local influence while still using several neighbors. Visualizations are useful for two-dimensional examples, but model selection should ultimately be based on validation performance and the needs of the problem. A single train and validation split can produce a fragile estimate of model performance. One split may be unusually easy, another may contain more difficult or noisy observations. If we select k based on only one validation subset, the result may depend too heavily on that particular random partition. Cross-validation evaluates the model across several partitions. This provides a more reliable picture of how the model may generalize. The final test set should still remain separate from this tuning process. The letter k appears in two different concepts. In nearest neighbors, k is the number of neighbors used to classify a query point. In k-fold cross-validation, k is the number of partitions used to evaluate the model. These values are unrelated. We might evaluate a KNN model with 7 neighbors using 10-fold cross-validation. In that example, 7 controls the classifier's neighborhood, while 10 controls the validation procedure. In 10-fold cross-validation, the training data is divided into 10 folds. The model trains on 9 folds and is evaluated on the remaining fold. The process repeats until each fold has served as the validation set once. Stratified k-fold preserves approximately the same class proportions in each fold. Because scaling is inside the pipeline, standard scaler is fitted separately within each training portion. This prevents validation data from influencing preprocessing. The cross-validation scores show how performance varies across the folds, not only the average result. We can evaluate a range of neighbor values with cross-validation. For each k, calculate the mean validation accuracy. The misclassification error is 1 minus that accuracy. We then select a value near the lowest validation error. It is better to call this misclassification error rather than MSE, because MSE usually means mean square error in regression. The error curve may contain several values with similar performance. In that situation, we can consider model stability, simplicity, computation, and performance variation across folds rather than choosing from the average alone. GridSearchCV can evaluate combinations of hyperparameters. In this example, it tests several odd neighbor values, uniform and distance-based weights, and Manhattan or Euclidean distance. The double underscore notation identifies a parameter belonging to the classifier step inside the pipeline. Every candidate configuration is evaluated with the same cross-validation strategy. After fitting, GridSearchCV stores the best performing configuration and refits it using the complete training set. The final test set has not yet been used, so it remains available for an unbiased final evaluation. After selecting the hyperparameters, we evaluate the best pipeline ones on the untouched test set. We generate test predictions and calculate classification metrics. Accuracy provides an overall summary. The confusion matrix shows the types of correct and incorrect predictions. Precision, recall, and F1 score provide class-specific information. The test result estimates how the tuned model performs on observations that did not influence scaling, training, or parameter selection. We should avoid returning repeatedly to the test set to make additional tuning decisions. KNN and logistic regression should be compared under the same conditions. Use the same dataset, training observations, cross-validation faults, preprocessing strategy, and evaluation metrics. KNN creates local predictions based on nearby observations and can represent flexible nonlinear boundaries. Logistic regression learns a global parametric relationship and often produces a smoother decision boundary. KNN may perform better on some datasets, while logistic regression may perform better on others. A narrow difference in average accuracy does not prove that one algorithm is universally superior. We should also compare variation across folds, class-specific metrics, prediction speed, interpretability, and the requirements of the application. Let's summarize Chapter 9. K, nearest neighbors, classifies a new observation by finding nearby level training examples and using their classes to vote. Euclidean distance is a common similarity measure, but distance depends on the selected features, units, and metric. Feature scaling is essential because large numerical ranges can dominate the distance calculation. A very small k can create a complex boundary with high variance and overfitting. A very large k can oversimplify the problem, producing high bias and underfitting. Cross-validation gives us a more reliable way to select k than one train and validation split. GridSearchCV can tune the number of neighbors, weighting method, and distance configuration while preserving preprocessing inside the pipeline. After tuning, the final model should be evaluated once on unseen test data. KNN is intuitive and flexible, but prediction can become expensive because it must compare queries with stored training examples. It can also become less effective as the number of dimensions grows and distances become less informative. When comparing KNN with logistic regression, use the same data, folds, preprocessing, and metrics. The best algorithm depends on the dataset and the real requirements of the problem. For week 8, complete the assigned reading, watch the lecture and demonstration materials, finish the guided practice lab activity, complete the independent practice assessment, and continue your assigned Google Professional Certificate work. In the next week, we will move from supervised classification to unsupervised learning and discover groups in unlabeled data using k-means clustering.